How to interpret IIR filter pole zero plots in signal processing. Have you ever looked at a pole zero plot and wondered what it all means? Understanding these plots is essential for anyone working with infinite impulse response filters in signal processing. Let's break it down in a straightforward way. First, let's clarify what poles and zeros are. Poles are points in the complex z-plane where the filter's transfer function becomes infinite. They are found by solving the denominator of the transfer function. On the other hand, zeros are points where the transfer function equals 0, corresponding to the roots of the numerator. Now, picture the z-plane as a two-dimensional space. The horizontal axis represents the real part, while the vertical axis represents the imaginary part of the complex variable. A key feature in this plane is the unit circle, which is where the magnitude of z equals 1. Evaluating the filter's transfer function on this circle reveals the frequency response of the filter. When it comes to stability, it is crucial for an infinite impulse response filter to be bounded input, bounded output stable. This means all poles must be strictly inside the unit circle. If any poles lie on or outside the unit circle, the filter may become unstable or only marginally stable. And like poles, zeros can be positioned anywhere in the z-plane without affecting stability. Next, let's talk about frequency response. To find the frequency response, we evaluate the transfer function on the unit circle, where z equals e raised to the power of j times omega. Here, omega represents the normalized angular frequency. Poles that are close to the unit circle can create peaks in the frequency response, which enhance certain frequencies. Conversely, zeros near or on the unit circle can create dips, attenuating specific frequencies. The angular position of poles and zeros indicates the center frequency of their influence, while their distance from the origin relates to bandwidth and sharpness. This means that the closer a pole is to the unit circle, the sharper the response at that frequency will be. When engineers look at pole zero plots, they can quickly determine the type of filter they are dealing with, whether it is low pass, high pass, band pass, or notch. For example, placing zeros on the unit circle at specific angles can create notch filters that reject certain frequencies. Similarly, poles positioned near the unit circle can create resonances at specific frequencies. In practice, designing an infinite impulse response filter often involves specifying desired pole and zero locations to meet specific frequency response criteria. The coefficients of the filter's difference equation are derived from the polynomial factors that correspond to these poles and zeros. It is also essential to verify that all poles remains inside the unit circle after any changes, such as coefficient quantization. To summarize the interpretation process, start by identifying the poles and zeros on the complex plane. Check the locations of the poles relative to the unit circle to ensure stability. Then, map the angles of the poles and zeros to their corresponding frequencies to understand which frequencies will be emphasized or attenuated. Finally, assess how close they are to the unit circle to estimate the sharpness and bandwidth of the frequency features. Understanding pole zero plots is fundamental in digital signal processing, allowing for effective design, analysis, and troubleshooting of infinite impulse response filters in various applications, including audio processing, communications, and control systems.